Welcome to chemistry, the common ion effect. This is one of the most practical applications of Le Chatelier's principle in equilibrium chemistry. Imagine adding more of an ion that is already present in a solution at equilibrium. What happens? The equilibrium shifts to oppose this change, reducing the dissociation of the weak electrolyte. This seemingly simple idea has profound implications. It controls the solubility of salts, regulates the pH of buffer solutions, and is used in everything from water treatment to analytical chemistry. In this presentation, we will explore the fundamental principle, the mathematical treatment using ice tables, the effect on solubility, its role in buffer systems, and real-world applications ranging from qualitative analysis to physiological buffering. Through 5 quiz questions and 5 fully worked problems, you will master how to predict and calculate the common ion effect. The common ion effect is a direct consequence of Le Chatelier's principle. Consider a weak acid HA in water establishing equilibrium. HA plus H2O yields H3O plus A minus. The position of this equilibrium is determined by the acid dissociation constant Ka. Now, what happens if we add a salt such as NaA, which supplies additional A- ions? The system experiences a sudden increase in the concentration of A-, a product of the equilibrium. To relieve this stress, the equilibrium shifts to the left, consuming some of the excess A- by recombining it with H3O+ to form undissociated HA. The result is a decrease in H3O+ concentration and therefore an increase in pH. The weak acid becomes even less dissociated. The term common ion refers to the ion shared by both the weak electrolyte and the added salt. Let us visualize the mechanism on a molecular level. In a 0.10 molar acetic acid solution, approximately 1.3% of the acid molecules are dissociated into H+ and acetate ions. The vast majority remain as undissociated CH3COOH. When we add sodium acetate, we introduce a high concentration of acetate ions into the solution. According to the law of mass action, the reaction quotient QC becomes larger than Ka. The system must consume acetate and H+ to restore equilibrium. The reaction proceeds until QC equals Ka again. The net result is a much lower H3O+ concentration and an even smaller percentage of dissociation. With enough acetate added, the dissociation can be suppressed to less than 0.01%. This is the common ion effect in action. We have effectively pushed the equilibrium toward the undissociated form. The common ion effect has a dramatic impact on the solubility of sparingly soluble salts. Consider silver chloride, AgCl, in water. AgCl solid yields Ag++ Cl-, with Ksp equals 1.8 times 10 to the negative 10. In pure water, the molar solubility is about 1.3 times 10 to the negative 5 molar. Now, if we add NaCl to the solution, we introduce a high concentration of chloride ions, a common ion. The equilibrium shifts to the left, precipitating more AgCl solid. The solubility decreases dramatically. At 0.10 molar NaCl, the silver ion concentration drops to just 1.8 times 10 to the negative 9 molar. That is about 7,000 times less soluble. This principle is used in qualitative analysis to selectively precipitate one ion while keeping another in solution. It is also the reason why adding HCl to a solution containing silver ions produces an immediate precipitate of AgCl. Buffer solutions are perhaps the most important application of the common ion effect. A buffer is precisely a solution that contains a weak acid and its conjugate base, the common ion. The weak acid HA provides a reservoir of the acid form, and the conjugate base A- from a salt like Na provides the common ion that suppresses HA dissociation. This combination creates a solution that resists pH change. Applying the common ion effect mathematically, we use the Henderson-Hasselbalch equation. If we have 0.10 molar acetic acid and 0.10 molar sodium acetate, the presence of acetate from the salt suppresses the dissociation of acetic acid so effectively that the concentration of HA remains essentially unchanged from its initial value. The pH is calculated as pKa plus log of A minus over HA, giving 4.76. This is much higher than the pH of 2.87 that pure 0.10 molar acetic acid would have. The common ion effect is what gives buffers their pH stability. The common ion effect has numerous practical applications. In qualitative analysis, the selective precipitation of ions relies on controlling the concentration of a common ion. For example, in group I analysis, HCl is added to precipitate AgCl, PbCl2, and Hg2Cl2, while other metal chlorides remain soluble. In water treatment, fluoride is added to drinking water to suppress the dissolution of tooth enamel, which is hydroxyapatite. The fluoride ion replaces hydroxide to form fluoroapatite, which is even less soluble and more resistant to acid attack. In industrial chemistry, the common ion effect is used to maximize precipitation of desired products in processes like the Solvay process for soda ash production. In medicine, the calcium phosphate equilibrium in bones is regulated by the common ion effect, with calcium and phosphate ions in blood at controlled concentrations to prevent bone dissolution. The common ion effect is analyzed quantitatively using an ICE table exactly like any other equilibrium problem. Consider 0.10 molar acetic acid with Ka equals 1.8 times 10 to the negative 5, to which we add sodium acetate to make the initial acetate concentration 0.050 molar. We set up the ICE table with initial concentrations. HA is 0.10, H plus is approximately 0, and A minus is 0.050. The change is minus X for HA, plus X for H plus, and plus X for A minus. Equilibrium concentrations. HA is 0.10 minus X, H plus is X, A minus is 0.050 plus X. Substituting into Ka equals X times 0.050 plus X divided by 0.10 minus X. Since Ka is small, X will be very small compared to 0.10 and 0.050, so we approximate. Ka equals X times 0.050 divided by 0.10. Solving gives X equals 3.6 times 10 to the negative 5 molar. Percent dissociation is only 0.036% compared to 1.3% without the common ion. This demonstrates the powerful suppression effect. Quiz question 1. The common ion effect is best described as what? Option A, the dissociation of a salt in water. Option B, the suppression of dissociation of a weak electrolyte when a common ion is added. Option C, the increase in solubility when a salt is added. Option D, the neutralization of an acid by a base. The correct answer is option B. The common ion effect refers to the shift in equilibrium that occurs when an ion already present in the equilibrium system is added from an external source. This suppresses the dissociation of the weak electrolyte. For example, adding acetate ions from sodium acetate to a solution of acetic acid shifts the equilibrium Sa to H++ A minus to the left, reducing dissociation. Quiz question 2. If NaCl is added to a saturated AgCl solution, what happens? Option A, more AgCl dissolves. Option B, no change in solubility. Option C, AgCl precipitates. Solubility decreases. Option D, the solution turns yellow. The correct answer is option C. Adding NaCl introduces Cl- ions, a common ion in the AgCl equilibrium. According to Le Chatelier's principle, the equilibrium shifts to the left to consume the excess Cl-, causing more AgCl to precipitate. The molar solubility of AgCl in 0.10 molar NaCl is only 1.8 times 10 to the negative 9 molar, compared to 1.34 times 10 to the negative 5 molar in pure water. Quiz question 3. A buffer resists pH change due to the common ion effect. Which equation directly describes this? Option A, Ka equals H plus times A minus divided by HA. Option B, pH equals negative log of H plus. Option C, pH equals pKa plus log of A minus over HA. Option D, Kw equals H plus times OH minus. The correct answer is option C. The Henderson-Hasselbalch equation, pH equals pKa plus log of A minus over HA, directly describes the common ion effect in buffers. The presence of the conjugate base A minus from a salt suppresses HA dissociation, and this equation calculates the resulting pH from the ratio of the two species. Quiz question 4. For the equilibrium PbCl2 solid yields Pb2 plus 2Cl minus, adding HCl will do what? Option A, increase Pb2 plus concentration. Option B, decrease Pb2 plus concentration. Option C, have no effect on Pb2 plus concentration. Option D, double Pb2 plus concentration. The correct answer is option B. Adding HCl introduces Cl- ions, which are a common ion in the PbCl2 equilibrium. The equilibrium shifts to the left to consume the excess Cl-, precipitating more PbCl2 solid and decreasing Pb2 plus concentration. This is the common ion effect on a sparingly soluble salt. Adding any soluble chloride salt will reduce the solubility of PbCl2. Quiz question 5. The percent dissociation of 0.10 molar CH3COOH with Ka equals 1.8 times 10 to the negative 5 is what? Option A, 1.3%. Option B, 0.13%. Option C, 13%. Option D, 0.013%. The correct answer is option A. For a weak acid alone, percent dissociation equals X divided by C times 100%. X equals the square root of Ka times C, which equals 1.34 times 10 to the negative 3 molar. Percent dissociation equals 1.34 times 10 to the negative 3 divided by 0.10 times 100%, giving 1.34%. When a common ion like acetate from sodium acetate is added, this percentage drops dramatically to about 0.036% or less. Problem 1. Calculate the pH and percent dissociation of 0.25 molar HF in a solution that also contains 0.10 molar NaF. Ka of HF equals 6.8 times 10 to the negative 4. Step 1. Set up the ice table for HF to H++ F-. Initial concentrations. HF is 0.25, H plus is 0, and F minus is 0.10 from the AF. The change is minus X plus X plus X. Equilibrium, 0.25 minus X, X, and 0.10 plus X. Step 2. Write Ca equals X times 0.10 plus X divided by 0.25 minus X equals 6.8 times 10 to the negative 4. Step 3. Since Ca is small, X will be much less than 0.10 and 0.25. Approximate. Ca approximately equals 0. 10x divided by 0.25. Step 4. Solve for X. X equals 6.8 times 10 to the negative 4 times 0.25 divided by 0.10, giving 1.70 times 10 to the negative 3 molar. Step 5. Check the 5% rule. 1.70 times 10 to the negative 3 over 0.25 equals 0.68%, which is less than 5%. The approximation is valid. Step 6. pH equals negative log of 1.70 times 10 to the negative 3, which equals 2.77. Percent dissociation is 1.70 times 10 to the negative 3 over 0.25 times 100%, giving 0.68%. The answer? pH equals 2.77 and percent dissociation equals 0.68%. Problem 2. Calculate the molar solubility of BaSO4 in 0.010 molar Na2SO4. Ksp of BaSO4 equals 1.1 times 10 to the negative 10. Step 1. BaSO4 solid yields Ba2++ SO4 2-. Initial from Na2SO4. Sulfate concentration is 0.010 molar. Let's equal the molar solubility of BaSO4. Then Ba2+ equals S, and SO4 2- equals 0.010 plus S. Step 2. Ksp equals S times 0.010 plus S equals 1.1 times 10 to the negative 10. Step 3. Since Ksp is tiny, S is much less than 0.010. Approximate 0.010 approximately equals 1.1 times 10 to the negative 10. Step 4. S equals 1.1 times 10 to the negative 10 divided by 0.010, which equals 1.1 times 10 to the negative 8 molar. Step 5. In pure water, the solubility would be the square root of Ksp, which is 1.05 times 10 to the negative 5 molar. The solubility ratio is approximately 1 over 1,000. The answer? The molar solubility is 1.1 times 10 to the negative 8 molar. Problem 3. A solution contains 0.40 molar NH3 and 0.20 molar NH4Cl. Calculate the pH. Kb for NH3 equals 1.8 times 10 to the negative 5. pKa of NH4 plus equals 9.25. Step 1. This is a basic buffer. NH4Cl provides the common ion NH4+, which suppresses NH3 dissociation. Step 2. Use the Henderson-Hasselbalch equation for base buffers. pH equals pKa plus log of NH3 over NH4+. Step 3. pKa of NH4+ is 9.25. Step 4. pH equals 9.25 plus log of 0.40 divided by 0.20. Step 5. pH equals 9.25 plus log of 2. Log 2 is 0.30. The answer, pH equals 9.55. This is a basic buffer with pH above 7. Problem 4. Will a precipitate form when 25.0 milliliters of 0.010 molar AgNO3 is added to 25.0 milliliters of 0.020 molar NaCl? Ksp of AgCl equals 1.8 times 10 to the negative 10. Step 1. Dilute both solutions since volumes add to 50 milliliters. Egg plus concentration equals 0.010 times 25.0 divided by 50.0, giving 0.0050 molar. Cl minus concentration equals 0.020 times 25.0 divided by 50.0, giving 0.010 molar. Step 2. Calculate Q equals Ag plus times Cl minus. Q equals 0.0050 times 0.010, which equals 5.0 times 10 to the negative 5. Step 3. Compare Q to Ksp. Q equals 5.0 times 10 to the negative 5, which is much greater than Ksp of 1.8 times 10 to the negative 10. The answer? Yes, a precipitate forms immediately because Q greatly exceeds Ksp. The common ion Cl- drives the equilibrium far to the left, causing precipitation. Problem 5. Calculate S2 minus concentration in a saturated H2S solution of 0.10 molar at pH 3.0. Ka1 equals 9.5 times 10 to the negative 8. Ka2 equals 1.0 times 10 to the negative 19. Step 1. At pH 3.0, H plus concentration equals 10 to the negative 3.0, which is 1.0 times 10 to the negative 3 molar. The H plus from pH adjustment is the common ion that suppresses S2- formation. Step 2. The overall equilibrium constant K equals Ka1 times Ko2. K equals 9.5 times 10 to the negative 8 times 1.0 times 10 to the negative 19, giving 9.5 times 10 to the negative 27. Step 3. K equals H plus squared times S2 minus divided by H2S equals 9.5 times 10 to the negative 27. Step 4. Solve for S2 minus. S2 minus equals K times H2S divided by H plus squared. Step 5. S2 minus equals 9.5 times 10 to the negative 27 times 0.10 divided by 1.0 times 10 to the negative 3 squared. The answer, S2 minus concentration equals 9.5 times 10 to the negative 23 molar. The common ion H plus massively suppresses S2 minus formation. Let us consolidate everything we have learned. The common ion effect is the shift in equilibrium caused by adding an ion already present in the system. It is a direct application of Le Chatelier's principle. The dissociation of a weak electrolyte is suppressed when a common ion is added from a soluble salt. This effect is quantified using ice tables and equilibrium expressions. For sparingly soluble salts, adding a common ion dramatically reduces solubility through the KSP expression.